We are taking chapter number 23, testing conventional applications. Deriving the test cases. So how do we find out number of test cases? How to make test cases? In design, we might write some flow chart, draw some data flow diagrams, write some algorithm, how the program is going to be actually coded. So these all the inputs can be converted into a graph, and that can be converted to graph. Graph can give you, we can evaluate from graph number of test cases. So this is a simple algorithm called average. You add the numbers and divide by the count of the numbers. And how do we actually make a graph? Now you may ask why we are making a graph, why we are not using only this code or the algorithm. You will see that it is easy to find out from this graph the cyclomatic complexity. And this cyclomatic complexity is nothing but the upper bound of number of test cases we need to generate. And what will be the test cases? The only underlying idea is the paths we are taking. All the paths should be executed at least once. So don't go into the detail of this average code. I'm just showing you that because we have to make a control flow graph, we have to make certain nodes and edges. Please note, all the nodes mainly are concerned with the equivalent analogous diamond of the flow chart. Diamond is all about conditional statement. If, else, switch, do, while, for, and case, switch case. Okay. These are round circles called the nodes, and these nodes specifically we give for the conditional statement, and then the say accompanying or simple say lines like addition lines or some printing lines. So this one from I equals 1 till do, while I equals 1 till sum equals 0, these are just declaration or initialization. But we have to worry about do while. So from I equals 1 to do while, we can regard all this as node number 1. As I said, we are just interested mainly in the conditional statement because that will be the branching and we have to test the branch. Now inside this do while, we have two different testings or checking, and then we have an AND operator. So this we have a compound statement. So we will take first one and second one because both the condition will either be true or false. So we'll take the first one as 2 and second one as 3. So now we have got 3 nodes. The first node for do while and others. Second is for this checking before and third is for the checking after the AND operator. Now after 2, 3 is coming, but from 2 and 3 there will be branching because the condition can be yes or no or true or false. Now when it ends, you have to go to the end because 2 and 3 are the simple path, but if it is not taking that path, it will go to 10, and 10 is what? After end do. Now coming to the fourth, you want to write it, you can write it, make a node, you can make it doesn't matter because you can combine this 4 with 3, you can also combine this 4 with 5. So this 4 has no value in this kind of scenario. Now coming to the next if. In this if also we have 2 and before and after and. Now it is up to you if you want to take this if. If you want to take this if also as a node, you can take. We are not taking if as a node, but if you want, you can take it. So your graph and my graph may be different. Now I'm taking just this value greater than equal to minimum and value less than equal to minimum. Now when if is okay, when it fails, whether it is going to go, it is going to go to 8 and if. So we pointed it to 8. Now after 8, there will be 9, that is the do while will end. So we are going to end do. As I said, every edge has to start and end. Now when this is going on, if the conditions are not met, you have to go again back to 2. So from 9 you have to go back to 2, and this will go on because do while go on and on until the condition is false. From 8 you will go to, see, this 8 to 9. From 6, where are we going? If the condition is true or false, we are going to 7 or 8. Okay, either if is true or if is false. So that is, we are going to from 6 to 8 and 7. So this is the way. One more thing is from 10. If 10 is true, we go to 11. If 10 is false, we go to 12, and then we end at 30. This is end if. Now if you even don't understand a bit, you just have to take the conditional statement and just see and just make the edge from where it starts and where it ends, and name those nodes as some numbers. Okay. So the basis part testing method can be applied to a procedural design or a source code or a flow chart or a data flow diagram. Whichever input you have, you just see the conditional statement and the compound statement and name them as the nodes and join them. So this was the average simple algorithm, and this has a compound conditions and loops. So we took it for the example of test case design. So what are the steps? First step we have already done. Using this design or a code as a foundation, we actually made a control flow graph, and we use the symbols and construction rules. And the construction rules, you can just, manipulate it, change it, because ultimate our aim is to execute all the paths exactly at least once. Okay. So 10 you can take if in after 4, if we have not taken, you can take it. So wherever it starts, take a node. Wherever it ends, you can have another node. Okay. So this is a kind of graph we made. Now we know how to find out the cyclomatic complexity. Since we have the control flow graph, now we have simple formula to find out the cyclomatic complexity. Cyclomatic complexity is just the number of cases, or you can say the upper bound. So VG, all this we are going to find out cyclomatic complexity. This can be determined without developing a flow graph. Just count the conditional statement in the PDL or the flow chart or the data flow diagram. How many conditional statements are there? Just count it. Just add a 1 to it, and then that will be your number of cases. The only thing this flow graph is helping you is now you can visually see how many paths are possible, whether these are independent paths or not. Otherwise, you don't have to make this control flow graph, just count the conditional statement, add a 1. But since we are following a formal procedure, let us see how we can compute the cyclomatic complexity, which will be actually the number of cases you have to make. How many regions are here? This is the first region, second region, these are the closed region I am talking about. Third region, and this is the fourth region, this is the fifth region, these are all the closed region. One region is outside, which is the open region. So how many regions we have? We have 6 regions. So these are the number of test cases, or this is the cyclomatic complexity. The second way to find out is E minus n plus 2, number of edges minus number of nodes, plus to compute all these, and just add 2 to it. 17 minus 13 plus 2 is 6. So again you are getting the same thing, 6. How many predicate nodes are there? Predicate nodes are there, or those nodes from where 2 or more arrows are coming out. 1, 2, 3, 4, 5. Okay. 5 predicate nodes are there. Just add a 1 to it, and that will be 6. So this is a check also. You have 3 formula, and they will check that okay, we have got 6 as the cyclomatic complexity, and these are the upper bound of number of test cases you have to make. And then we have to determine a basis set of linearly independent path. Why we are making basis set? You said we have computed already the cyclomatic complexity. Because we know the cyclomatic complexity or the number of test cases, what will be the test cases? You have to write those test cases. You have to execute that test cases. So for that, you need to know that which nodes or which conditional options you are going to take. And these are nothing but the path, independent path. Independent path is that if you have checked if x is greater than 0, now you will check if x is less than 0. You will not check if x is greater than 0 again and again. If x is greater than 0, what will happen is one path. If x is less than 0, is another path. So this is the cyclomatic complexity. We are going to find out the path because we already know that the cyclomatic complexity is 6. We'll make 6 paths. So see, 1, 2, then we go to 10, then we go to 11 and 13. This can be one path. Always the first path you choose will be unique because you didn't have any other path. Now you make a second path. 1, 2, 10, go to 12 and 13. Now this is again a unique path because if you see here, the first path you have included 11, second path you have included 12. So these are 11 and 12 are different edges you have included. And that is what we want. Independent path means every time you have to have a special unique edge or the condition or the branch or the control structure included. Let us take one more. 1, 2, 3, 10, 11, 13. Now this again is there because we started with 1 and 2 and then went to 10 for first two paths. But second one we went up to 3. 1, 2, 3 and then we went to 10, 11, 13. Now we have these multiple paths and these are all unique paths and all these we have already explained, but these are the paths you can check. Just see that you don't go to or you don't repeat the path again and again. Just independent path, your unique path, unique route, unique branching, and that is the essence of making the test cases. Test cases cannot be redundant. Test cases need to be unique and they need to find out whole class of error. This ellipsis is indicating that any path through the remainder of the control structure, we can accept it. We can have any after 2. We can have any after 2. As we discussed earlier, just compute the predicate node and just add 1. You will know how many test cases are there. You can find out the cyclomatic complexity also. But the whole idea is after finding the cyclomatic complexity, you have to know the paths also because ultimately you are going to write those test cases. Finally, we are ready for the preparing of the test cases that will force execution of each path in the basis set. Again, I am telling you, the tester, when he is going to test all the test cases, he is sure that all the statements in the program have been executed at least once and any problem in any of the path is the test case result. So if this is not working properly, any of the independent path, there is an error and that error has to be fixed, that error after the testing. And there are some independent path, there may be certain path where it cannot be tested in a standalone fashion. It requires some other stub or the driver or whichever you say. Some component have to be made, some code has to be written. So for that you can make this path as a part of another path. For example, you have 6, make it at 5, add a 1 to another. Graph matrices. Now, in order to understand the control flow graph, because control flow graph is all about making it from the flow chart, making it from the PDL, program definition language or design language, then you have made it from say algorithm or a data flow diagram. So whichever input was there in your design or while you are modeling the requirement, making it for the coding, before the construction goes, we have all these conditional statement and all the compound statement we included. We converted them into the nodes and the edges, and finally we made a control flow graph. Now I already told you, you don't have to make this graph if you don't want, because you just have to compute the cyclomatic complexity, and plus that cyclomatic complexity will give you the test cases. But this data structure which you see here is graph matrix. This is assisting the basis path testing. How does it help? Now we cannot do the exhaustive testing. So the graph which we are making through this control flow graph we are making a matrix, and this matrix will give you a clear idea, or the user or anybody else. I'll make a matrix from this flow graph. Okay, I'm making a graph matrix, which is essentially the same as what you see on right. So how many nodes are there? How many round circles are there? 5. So 5 nodes are there. So for that we'll take 5 rows and 5 columns. These are the rows I'm numbering. Now I'm going to make again 5 columns. So how many nodes are there? You need to make a square matrix, that is the row and column has to be same, and those should correspond to the number of how many nodes we have. So these are node, and the other one you can just name it as connected to the node. So you have given the number to every node. You can give anything. You can give the Roman values. It doesn't matter. But right now in this example we are taking the node as numbers, and the edges we have used letters. Again, you can take any of these. You can write your name also. We are giving letters. Okay. Why we are giving this? Because we just need to know which edge is connected, which node is connected to which node by which edge. That is the only thing this graph matrix is giving you. So you'll ask, what is the fun? What is the benefit? I'll just tell you. You'll see the benefit. First of all, 1 is connected to 3, so put 1 and 3 interaction is A. 3 is connected to 4, we wrote B to the intersection of row and column. 2 is connected to 4, 3 is connected to 4, we have already done. Now 2 is not connected to 4, 2 is not connected to 5, 4 is connected to 2, so put a C. 5 is connected to 2, see 2 is not connected to 5, 5 is connected to 2. That is how we'll go about it. 5 arrow 2 will make put intersection from 5 to 2. And then we have 5, 3. Again we have 4 is connected to 5. So 4 is connected to 5. This is how we are going to write. And then D is also remaining. So 3 is connected to 2. So we put a D. Now this whole graph has been made. So this graph is quite simple to make, but the essence is these are the edges being connected. There is another way generally people make it. They don't want to give the alphabets. They just want to give 1 here. If one node is connected to another node, then they give 1 here. You just replace 1 here. And other points, other cells are given 0 value. Normally we don't write 0 because it will make it quite clumsy and difficult to handle the row and columns. So they just put 1, and we are also going to put 1. We don't put 0. Now all these values A, B, D, C, G, E, F, they can be replaced by a weight. For example, there is a probability that 5 and 3, this edge is going to execute higher. This is the number of times this is going to execute is higher than the other values. So what we will do is we will put at E, for example, take D also. So we have a probability. So I'll put 0.8 here, and for others we can put 0.2 or 0.1. What does it mean is that I will just check 3 and 2 and 5 and 3. I hope you got the idea. I'll give you one more idea. If the processing time during a traversal of link, we are more interested in the processing time, or you are more interested in memory during the traversal of link. When you are checking memory, for example, 3 and 4, it is 3 and 4 is B. So now I will give a higher value to this 3 and 4, the cell which is intersecting 3 and 4, and others I leave. So I will just test 3 and 4 more prominently. Others I may leave, or I can check one or two more. The resources also, I can give a weight here and then check that thing. I can leave others because there can be plenty of test cases. Because I am interested in memory or resources, I will check only that have a higher weight which I have assigned, or my program leader or manager has assigned. I hope you got the idea. That is why the weights are important. This graph is assisting the basis part testing. The numbers which we give will signify whether we have to test it or we can just test it later, or we can leave it. That is the option. That is the option. Okay, this control structure testing we are going to see in the next discussion. Till then, thank you so much. Take care of yourself.